The small particle reagent method involves spraying of a suspension on the latent fingerprints. The beauty of this method is that it can detect fingerprints on a very large number of crime scene evidence. Mostly they are non-porous, but even on porous substances, this method gives good results. In this case, we use a suspension of molybdenum disulphide in water to which a few drops of detergents are added. The detergent is added in order to delay the sedimentation of molybdenum disulphide. Since the disulphide is insoluble in water, it remains suspended, but over a course of time, it tends to settle down, and this settling down is delayed in presence of any surface active substance, which, as I said, is the detergent in this case. This method is quite old, and its main application is that it detects fingerprints on moist surfaces. These days, the criminals are educated and they know that after committing the crime, they might be caught on the basis of fingerprint evidence. So they endeavor to destroy the fingerprints before leaving the scene of crime. And one such method is to spray water on the crime scene. Sometimes they don't even have to do that. The crime scene is outdoor, it is raining, or the humidity is high and the fingerprints get washed out. But with small particle reagent method, which we generally abbreviate as SPR method, this problem is avoided. Even if the surface has remained immersed in water for quite a few hours, this method still develops fingerprints. The molybdenum disulphide reagent had a few limitations. Firstly, it's quite costly. Secondly, it's a bit toxic. And thirdly, this reagent is dark grey or tending to be black in color. So that if the crime scene evidence happens to be of dark color, the contrast is not very good. We have now tried to modify this method. Instead of molybdenum disulphide, we use zinc carbonate. The crystal size of zinc carbonate is comparable to that of molybdenum disulphide, so that also serves the purpose. Moreover, this is insoluble in water like molybdenum disulphide, so a suspension can be easily made. Zinc carbonate is white in color, and now there is no problem of developing fingerprints on dark colored items. But suppose the crime scene evidence itself is light color, say it's white or it's pink. Even then zinc carbonate serves the purpose because we can very easily mix some dye in it. We have used dyes like eosin yellow or basic yellow 40. And we can just manipulate it, we can use different dyes keeping in view the background color of the crime scene evidence. These dyes are fluorescent. So even if the prints which develop, they are faint, they are weak, we can enhance them using a suitable light source. Zinc carbonate is not only non-toxic, it is rather being used for medicinal purposes. Its cost is much less, at least 8 times less than that of molybdenum disulphide. And moreover, it is more easily available. It's there everywhere. Molybdenum disulphide one has to procure with some difficulty. We have seen that the prints which have remained immersed in water for even 36 hours can be easily developed by the small particle reagent using zinc carbonate and a dye. And of course, the detergent has to be added, and as I said earlier, the purpose of detergent is to delay the sedimentation. The small particles of this composition, whether it is molybdenum disulphide or it is a zinc carbonate, they actually physically interact with the fatty acid constituents of sweat, and they give sharp and easily identifiable prints on a large number of crime scene evidence.
Dear students, after studying this module, you shall be able to know that small particle composition detects latent fingerprints on a wide range of crime scene evidence. The technique is specifically useful on non porous items which have been accidentally or deliberately wetted. In its modified version, the small particle reagent shows fluorescent characteristics as a result of which it may detect weak and faint fingerprints. Now let us start this chapter with a brief introduction. Small particle reagent technique is used to detect latent fingerprints on non-porous crime scene evidence, including those that have been accidentally or deliberately wetted. Conventional small particle reagent is formulated by suspending a finely powdered insoluble binary salt, usually molybdenum 4 sulfide or titanium 4 oxide, in water containing a few drops of surfactant. A commercial liquid detergent is generally used as a surfactant. In modified small particle reagent, a luminescent dye is added to the composition. In either case, the insoluble salt adheres to the fatty components of the sweat residue. The small particle reagent technique is also referred to as wet powdering. SPR is usually used when processing wet surfaces and it adheres to the print. Once dry, it can be lifted off the surface using fingerprint lift tape and put on a lift card. With the tape, it can be sprayed right on the adhesive side of the tape and handled in several different ways. The first and the best method is to spray the tape and place it directly onto the latent print card using a sponge or paper towel. Squeeze over the tape and it will adhere to the card. The resulting latent print is of extremely good quality. Now let us see significance of small particle reagent technique. The most common base material used for formulating small particle reagent is molybdenum 4 sulfide MOS2, an insoluble binary inorganic salt of dark gray shade. When suspended in water containing a few drops of a surfactant and applied to a latent impression, the salt gets adsorbed on the sebaceous constituent of sweat residue. The salt is pulverized before preparing its suspension, and hence the technique is often referred to as wet powdering. The sebaceous sweat largely contains fatty acids, lipids, and glycerol derivatives. These biomolecules are quite stable and retain their composition in latent fingerprints for relatively long periods. Moreover, these are insoluble in water. For this reason, small particle reagent is able to detect fingerprints on those items which have remained immersed in water for varying time period. In actual crime cases, such a situation arises when the criminal sprays water on the crime scene after committing the offense. It is also possible that the crime scene may be an outdoor location and the physical evidence becomes exposed to high humidity or rainfall. In such cases, conventional methods fail to detect latent fingerprints. However, since small particle reagent technique is sensitive to insoluble sebaceous constituents of sweat, it works on such surfaces. In fact, this method has been used to detect fingerprints on vehicles being wet in rain or on glass, metal, and plastic items recovered from aquatic systems. It has also been used to develop fingerprints on water soaked firearms. The detection process does not interfere with subsequent ballistic analysis. Small particle reagent method works on containers which become contaminated by the commodity they hold. For example, soft drink cans and glasses are often wetted by the beverage. Regular powders, fail to detect fingerprint on such surfaces, but small particle reagent technique gives results. The powder method often fails to develop fingerprints on items which have a rough texture or an irregular shape. The reason is that the powder cannot be brushed to every nook and corner of such a surface. Yet, when the object is treated with a suspension, either by dipping or by spraying, the composition it touches every segment of the surface and chances of detecting fingerprints are far greater. The surfactant, also called as surface active agent, is an important component of small particle formulation. It has two functions. Firstly, it delays the sedimentation of the insoluble salt. Secondly, and more importantly, it ensures a uniform application of suspension on the surface. Usually, a commercial liquid detergent serves as a surfactant in small particle reagent formulations. Its concentration in the composition is critical to optimum development of fingerprints. If it is too little or too excess, the quality of prints is lowered. The fingerprints developed by molybdenum 4 sulfide based composition are dark gray in color. Proper contrast is not achieved if the background color of the surface is too dark. For such surfaces, molybdenum 4 sulfide is replaced by titanium 4 oxide. The crystal dimensions of the base material are critical for effective development of fingerprints by the small particle reagent method, and these parameters are comparable for molybdenum 4 sulfide and titanium 4 oxide. Since titanium 4 oxide is white in color, it gives a good contrast on dark surfaces. Other substitutes of molybdenum 4 sulfide are graphite, lead 4 oxide, PbO2, and cobalt oxide, CO2O3, a mixed iron oxide. Fe3O4 gives excellent contrast and clarity on smooth and non-porous items. Now, let us have a look on methodology. Molybdenum 4 sulfide is placed in water and a commercial liquid detergent, for example, Gentile or Easy, is added to the content. The suspension is agitated and transferred to a tray or a spray bottle. The surface bearing the latent fingerprints is either sprayed with or dipped in the small particle reagent formulation. On vertical surfaces, the reagent is sprayed directly above the region where fingerprints are likely to be present. As it drips down, it covers the latent impressions. It takes 1 to 3 minutes for the fingerprints to develop. Thereafter, the item is washed under a gentle stream of water for about 30 seconds to remove the excess material. The developed fingerprints are photographed. These are then allowed to dry, either under natural conditions or with the aid of a hair dryer. Finally, these are lifted by using the fingerprint tape. An advantage of small particle reagent technique is that after the fingerprints have been photographed and lifted, the surface may be rendered clean by wiping with moist cotton. No permanent stains are left on the surface after impressions have been developed. Now let us see modified small particle reagent. In the modified version of small particle reagent, molybdenum 4 sulfide is replaced by basic zinc carbonate, also called zinc carbonate hydroxide monohydrate. Its composition is ZnCO3, 2Zn OH 2, H2O. Besides the surfactant, a fluorescent organic dye is added to the composition. Since basic zinc carbonate is white in color, it gives a good contrast on dark colored surfaces. If the background color is pale or light, a good contrast can still be achieved by illuminating the developed prints with radiation of a suitable wavelength. The organic dye emits fluorescence and enhances the print. Its fluorescent characteristic of the stain also assists in developing fingerprints on multicolored surfaces. The commonly used luminescent organic dyes are eosin yellow, eosin blue, and crystal violet. Eosin is a fluorescent acidic negative compound that binds to and forms sols with basics or eosinophilic compounds containing positive charges, such as proteins that are basic, positive due to the presence of amino acid residues such as arginine and lysine, and stains them dark red or pink as a result of the actions of bromine on fluorescein. In addition to staining protein in the cytoplasm, it can be used to stain collagen and muscle fibers for examination under the microscope. Structures that stain readily with eosin are termed eosinophilic. Crystal violet or gentian violet, also known as methyl violet 10B or hexamethyl para-arosilene chloride, is a triaryl methane dye used as a histological stain, and in Graham's method of classifying bacteria, crystal violet has antibacterial, antifungal, and anthelmintic properties and was formerly important as a topical antiseptic. The medical use of the dye has been largely superseded by more modern drugs, although it is still listed by the World Health Organization. The name gentian violet was originally used for a mixture of methyl pararosaniline dyes, but is now often considered a synonym for crystal violet. The name refers to its color being like that of the petals of a gentian flower. It is not made from gentians or from violets. The fluorescent small particle reagent is prepared as follows: to a suspension of basic zinc carbonate in water, a fluorescent organic dye, and a commercial liquid detergent is added. The contents are thoroughly mixed. The suspension is sprayed on the surface bearing latent impression. This surface was earlier immersed in water for a specific period of time. After waiting for 1 minute, the item is washed under a gentle stream of water for 40 seconds and then dried with a hair dryer for 30 seconds. Clear and sharp fingerprints develop. The developed fingerprints are illuminated with radiation having 505 to 550 nanometer wavelengths. When observed through red goggles, the fingerprint shows fluorescence. A sample fingerprint developed by crystal violet based small particle reagent on aluminum foil which had been immersed in water for 5 days is depicted in the given figure. Another representative fingerprint developed by eosin blue based small particle reagent on aluminum foil that was exposed to water for 7 hours is shown in the figure. The small particle reagent containing eosin blue also develops fingerprints on several commercial brands of compact disc. The stored data is neither damaged nor erased when latent impressions are detected by this method. Moreover, new files may be added to the compact disk on which small particle formulation had been applied. A sample fingerprint developed on a compact disk is shown in the given figure. Basic zinc carbonate possess no occupational hazard to the user. In fact, it is used as an astringent and topical antiseptic. On the other hand, molybdenum sulfide, the base material used in conventional small particle reagent technique, is toxic. It is also more expensive than basic zinc carbonate. My dear students, now let us summarize this chapter. So, in this chapter, we have learned that small particle reagent is an efficient and sensitive technique to develop fingerprints on wet non-porous items. It gives good results even on dry surfaces. The method is simple and may be operated even by an amateurish hand. The modified small particle reagent has a further advantage since, due to its fluorescent characteristics, it can develop weak and faint fingerprints as well as latent impressions impinged on multicolored items. Along with it, in this chapter, we have come to know that the compositions have a relatively long shelf life of almost 6 to 8 weeks. Then, the fingerprints developed by molybdenum sulfide based compositions are dark gray in color. Proper contrast is not achieved if the background color of the surface is too dark. Along with it, we have learned that in the modified version of small particle reagent, molybdenum sulfide is replaced by basic zinc carbonate, also called as zinc carbonate hydroxide monohydrate. The small particle reagent containing eosin blue also develops fingerprints on several commercial brands of compact discs. The stored data is neither damaged nor erased when latent impressions are detected by these methods. Lastly, we have come to know that basic zinc carbonate possess no occupational hazard to the user. In fact, it is used as an astringent and topical antiseptic. On the other hand, molybdenum sulfide, the base material used in conventional small particle reagent technique, is toxic.